Okay, so let's continue our study of trigonometric identities even further. So besides those double angle and triple angle formulas, these are some other formulas that we will need to prove and then remember so that we can use them to solve problems. Now let us first see what these formulas tell us. It looks like a lot. Since we have to formulate some way of remembering, unfortunately you will have to remember these formulas, okay. It takes some time to derive them, and if you don't do it now, in the examination hall you won't be able to do it, okay. So you have to actually memorize these things, but of course that doesn't mean you will just have to keep on writing these things without without seeing how to memorize it effectively, okay. Let us see what all these formulas have in common. All of them have x plus y over 2 and all of them have x minus y over 2 as well. So these parts do not change. What change though are the functions themselves, cos and sine. So we just need to see in what pattern they are appearing. So if you have cos x plus cos y, it's an identity for cos x plus cos y. If both of them are cos, then here also you have cos. And one more thing that you should not forget is that in all these formulas, this factor of 2 is always appearing. So when you have both of them cos, you have both of them cos here. But if there is a plus, but if it is cos x minus cos y, then both of them are sine and there is a minus sign. However, if both of them are sine, then there are mixed terms, sine and cos both. Do you see where this is all coming from? You recall the formulae for cos x plus y. This is cos x cos y minus sin x sin y. So when it comes to cos, whether it's plus or minus, that's the different matter, okay. Let us first see that when both the terms are cosine terms, then either you have cos cos or sin sin. Which one will you have? That will depend on what the operation is. If it is addition, then it is cos cos. Why? Because that is the plus term here. If it is plus, if you have plus here, then it is cos cos. But if you have minus here, then it is sin sin, because that is the minus term. This way you can remember what the things are that are appearing. Also note one more thing, that because there is a minus sign, this you will have to remember specially, separately. Okay. So in only this one there is a minus sign. But at least one thing now is clear, and likely we will never forget, is that when we have both the terms cos, then either cos cos will appear or sin sin. And that too, when you have addition here, then cos cos appears because that's the plus term. And when you have subtraction, then sin sin appears, that's the minus term. But here you have to remember the minus. As opposed to this, what is the expansion of sin x plus y? This is sin x cos y plus cos x sin y. Okay. So when it is sine, when both the terms are sine, then mixed terms occur. You have sine as well as cos. It's however a little, it's a matter of remembering which one occurs in which, because this is the usual way of writing. That usually when we write the expansion of sin x plus y, we write sin x cos y plus cos x sin y. Why? That may also be decided by saying that because it is sin, so sin gets the first preference. So we start with sin x, but then cos has to come because cross terms are there. So, mixed terms are there in this expansion. So after sin x, you have cos y. And then the next one naturally is cos x sin y. Accordingly, when you have plus comes first, then the first, whatever you have here, that has the form of this term, sin cos. Sin x plus y over 2, cos x minus y over 2, and these two of course will be there. And then the next thing is minus. So for that, the second form has to be chosen. Cos comes first and then sin. Okay, so this way you may remember. Or you may formulate in your own way of remembering all these things. But whatever you do, you will have to memorize these formulas. Okay, let's now come to the proof of these formulas. And the proof actually will involve these expansions. And that is why the right hand sides look like that. Okay, so let's now start the proof. Because it's a little cumbersome to keep writing these ratios, so we give them some names. Let theta be x plus y divided by 2 and phi be x minus y divided by 2. Okay. Then what is theta plus phi? If you add theta and phi, of course the numerators will be added. So y and minus y will vanish and you will have 2x divided by 2. That means x. And similarly, when you subtract phi from theta, then you will have x plus y minus of x minus y. That means minus x plus y. So this time x and minus x will vanish and we will be left with 2y. And 2y divided by y is y. Alright. So now what are we going to do? You see, there is a, what do you think? What should we do in this case? To get these identities. It seems natural to start with the right hand side. Say you want to prove 1, the first one. It seems natural to start with the right hand side because here you can expand cos x plus y over 2, cos x minus y over 2, and then you can play with that and see if this comes or not. The same thing can be said about the other identities. But sometimes you can prove such things at once without proving them separately, separately presenting one proof for each one of them. You can combine things and sometimes that proves very fruitful because the proof will become very easy. In what way? You just think of this. Let us just think of the right hand sides of the first identity and second identity in terms of these new names. How do they look? Here it looks like this: cos theta, cos phi. And how does the right hand side here look? Minus 2 sin theta, sin phi. Does it ring a bell with you? You see, instead of simply starting with the right hand side of say 1 or 2 separately, why not we combine these two things? Because we can see that here we have cos theta, cos phi, and here we have sin theta, sin phi. So it should obviously give us something if we add these two right hand sides. In fact, if we just simply write this plus this means with the minus sign, what do we get? Let's see. So the proof, obviously after this, the proof continues from here. These things are just our observations. Now what we do, we straight away take these two things and add them up. 2 cos theta, cos phi minus 2 sin theta, sin phi. Don't simultaneously add these two also. Okay, we don't know that this is equal to this or this is equal to this. In fact, that's what we are going to prove. So we are not starting with an equation, we are starting with this expression. So this is what? 2 times cos theta, cos phi minus sin theta, sin phi. But this is precisely the but cos theta plus phi is. So 2 times cos theta plus phi. However, what is theta plus phi? X. So you get 2 cos x. You give this equation some number, say 1. Now we have to do something else also. This time we are going to subtract this from this. So because already there is a minus sign, so now it will turn into plus. Also, two cos theta cos phi plus 2 sin theta sin phi is equal to 2 times cos theta cos phi plus sin theta sin phi. And you know that this is 2 times cosine of theta minus phi, and theta minus phi is y. So you get 2 cos y. Now using these two relations, two equations 1 and 2, we can simultaneously prove these two things. And do you see why this is better than expanding say this as well as this? Because this is the product. Once you do such expansions and then you do multiplication, who knows what will come and whether you will be able to figure out or not that you are getting this and this. That is why this approach is much better, because it will give you it, whatever you want almost instantly. We are already almost there without having to perform any multiplication. But unfortunately, I have to clean this part. Alright, so now what shall we do? How shall we use 1 and 2? It's simple, no? Because we have already got cos x and cos y. So why not add 1 and 2 and see what we get? Adding 1 and 2, we get, and we are also going to write things a little differently. We will write cos x plus cos y on this side. So 2 cos x plus 2 cos y is going to give us what? You see, what should this side be? This side, of course, should be the expression that you started with. That means, for this one at least I am writing everything, but you need not write everything. You can straight away write what ultimately comes. Minus 2 sin theta sin phi plus this one, 2 cos theta cos phi plus 2 sin theta sin phi. So you immediately see that there is a cancellation. Minus 2 sin theta sin phi plus 2 sin theta sin phi vanish. And you are left with 2 cos theta cos phi, 2 cos theta cos phi, that is 4 cos theta cos phi. And this implies what? If you cancel 2 from both sides, you then have cos x plus cos y equal to 2 cos theta cos phi. But now if you write what theta and phi really are, you have got your identity. Because, so if we continue, theta is x plus y over 2 and phi is x minus y over 2. See how easy this is. In spite of all those complexity and everything, apparent complexity of course, but still, we did not have to multiply or do anything. By cleverly using both the identities, I should not say using both the identities, because we are going to prove it and we have proved one of them. By cleverly using parts of those identities together, we have been able to do this. Next, subtracting 2 from 1, we get, now we kind of have to recall what we had in 2 and 1. Well, actually it's not that difficult because we have 1 and 2 here. No? So what was 1? 1 was this, 2 cos theta cos phi minus 2 sin theta sin phi equal to 2 cos x. And this was the second one. 2 cos theta cos phi plus 2 sin theta sin phi equal to 2 cos y. So we will get 2 cos x minus 2 cos y, and this time we won't write it. Okay, we are going to straight away write what we will get. What shall we have? What will be the difference in this case? The difference will be that instead of this plus, we will have minus. What will happen then? 2 cos theta cos phi minus 2 cos theta cos phi will cancel out. They will cancel each other. However, minus 2 sin theta sin phi minus 2 sin theta sin phi this time will give you minus 4 sin theta sin phi. And now if you cancel 2 from both sides, you get cos x minus cos y equal to minus 2 sin theta sin phi, and that is why in the second identity this minus stays. Okay, it's there. And if you then write what theta and phi are, so you have got your second identity. It's that quick. Now let's see the third and fourth. Now to see what the third and fourth are, we have to do a little rough work because we do not have them here. The third one was this: sin x plus sin y equal to 2 sin x plus y over 2, that means theta, times cos x minus y over 2, that is phi. So this is one thing. And the other one, the fourth one, is this: 2 cos theta sin phi. So according to how we found these two, here also we should start with these things. Okay. So next means we have already found identities 1 and 2. So next, because all these things are in that single proof itself. Next, so this time first what we do, we take the sum of these two things: 2 sin theta cos phi plus 2 cos theta sin phi is equal to, I need not in fact again take 2 common out and do those things. If I straight away write, we have sin theta cos phi plus cos theta sin phi. So 2 times sin of theta plus phi, and this is 2 sin x. So this is your 3 and and 2 times sin theta cos phi minus 2 times cos theta sin phi. This will be 2 times sin of theta minus phi, which is 2 sin y. Okay, so say this is your 4. And so to get this identity, we have to add 3 and 4. 3 plus 4 implies some students have a habit of writing like this. Actually, we should avoid writing like this. When you are really writing a solution or say a proof nicely, formally, you should write adding 3 and 4 we get the following. This shows a kind of laziness that you do not really care about presentation. I am writing it like this here to save time, but you should not do that in the examination hall. But anyway, let's see what we are going to get. So this time also we will write the sin x and sin y terms on the left hand side. And let's see what type of cancel. Here also there will be a cancellation. 2 sin theta cos phi plus 2 sin theta cos phi will give us 4 sin theta cos phi. And 2 cos theta sin phi minus 2 cos theta sin phi will cancel out. And that's why after we cancel 2 from both sides, I am now kind of, do we need this 2? We started by considering these expressions, adding them, no? Do we need this 2? Because anyway we are cancelling 2 ultimately. I think we don't need this 2. This 2 is unnecessary here. In fact, if you do not have 2, there will be one line less. So you do that. Okay, but because I have already started it like this, so I am going to continue. So sin x plus sin y now is equal to 2 sin theta cos phi, and that just is x plus y over 2 times cos x minus y over 2. Yes, so that is our third identity. And finally, we are going to subtract the fourth equation from the third one. And that will give us what? That will give us this minus this. So this time 2 sin theta cos phi minus 2 sin theta cos phi, these two terms won't survive. And we will have 2 cos theta sin phi minus of minus 2 cos theta sin phi is plus 2 cos theta sin phi. So 4 cos theta sin phi. And that's how you have the fourth one. And that is equal to, if you write in terms of x and y again, not theta and phi, then you get your fourth identity. Okay, so there the proof is over. Okay, it's completed. Now, just like these 4 results, 4 identities, there are some other 4 identities that one can prove, which are in fact easier and comes straight from those addition formulae for sin and cos. That is sin x plus minus y and cos x plus minus y. So let's just mention those identities. And after that we will solve some examples where we are going to use these identities to do some things. But I do not see it here. Where are those examples? Yeah, I have it here. Okay, but before we see the examples, let us also see the identities in item number 21. So I am just going to straight away write all of them, not in any particular order, but let me start with cos, because there we started with cos. Cos x plus y plus cos x minus y is 2 cos x cos y. I am not going to make any further comment on how this is true. You just, of course, you can already see why this is true. You expand this one, and after cancellation, you are going to get this. Similarly, cos x plus y minus cos x minus y is equal to minus 2 sin x sin y. The third one is sin x plus y plus sin x minus y. This is 2 sin x cos y. And the fourth one, sin x plus y minus sin x minus y. This will be 2 cos x sin y. There is, of course, no need to even remember this. Once you are in a situation like this, you can, in fact, if you are well familiar with these expansions, individual expansions of sin x plus minus y, cos x plus minus y, you can mentally see what the thing is going to be. You think that I memorized these right hand sides. No, I just saw what it's going to be and I just wrote it. So now we can see some examples. And in fact, in the text also, it has been simply mentioned that one can prove these formulas, because the proof is straightforward, so it's not there in the text. So the first example is numerical. I am not going to give any numbers to these examples. Prove that three sin pi over 6 times secant pi over 3 minus 4 times sin 5 pi over 6 times cot pi over 4 is equal to 1. I say it's numerical because you are able to actually write these values. These are known angles, and that's why it becomes numerical and the answer should be 1. We have, if you want you can write left hand side equal to, but it's better to write like this, we have, instead of writing like left hand side equal to right hand side. Those things you used to do in lower standards, lower classes. Now you should write in a better way. So we have 3 sine pi over 6 times secant pi over 3 minus 4 sine 5 pi over 6 times cot pi over 4. So we will need to recall the known values. Some of them you already know from your school days, means from your say 9th standard or 8th standard, I don't exactly remember, where you get these trigonometric values for the first time, not these ones but these ones. But some of them you can immediately find from the definition itself using the unit circle. Okay. Now, in spite of us being told to always think of radians, because in our school days we actually memorized these values. Like sine 30 degree is 0.5, 1 over 2. So it's better to think of these angles in terms of degrees. For example, pi over 6 radian is actually equivalent to 30 degree, equal to 30 degree. So this is sine 30 degree. That means it is 1 over 2. What about the angle pi over 3 radian? That is equal to 60 degree. We can't think of secant immediately. Let's think in terms of cos. What is the value of cos 60 degree? Same, 1 over 2. But we do not have cos here. We have secant, which is the reciprocal of cos. And that's why we have 2 here. Minus, this has to be handled first of all, you have to do something here. Minus 4 times 5 pi over 6 is kind of a messy angle, but you can write this in place of 5 pi over 6, so that now you have known angles pi and pi over 6. Times, what about cos pi over 4? Pi over 4 radian is 45 degree. And we remember that tan 45 degree is 1. So its reciprocal cot 45 degree is also 1. So that means this term is 3 minus 4 times. Now you have already come across formulas for this type of expressions, sine pi minus something, and I told you to forget about those formulas, because you can actually immediately find what this thing is if you apply the sine a minus b formula or sine x minus y formula. It seems like it will be long, but actually it's not. You of course don't have to write these things down. You can do it mentally. Sine pi cos pi over 6 minus cos pi sin pi over 6. Sin pi is 0, cos pi is minus 1. Again, if you want to know why those things are true, you can go back to the unit circle. Pi corresponds to which point? This point on the circle. What are its coordinates? The x coordinate is minus 1 and the y coordinate is 0. The x coordinate is cos theta, y coordinate is sin theta value for this angle pi. And that's how cos pi is -1 and sin pi is 0. So that means this first term sin pi cos pi over 6 will vanish. And cos pi is -1, that minus and this minus will give you plus. So this is just sin pi over 6. Okay, and sin pi over 6 is already 1 over 2. So 3 minus 4 times 1 over 2, which will become what? After cancellation you will have 2 here. So 3 minus 2 is 1. So that's how you get 1. Okay, so that's the first one. Next, the more you practice, and by practice I don't mean you have to solve the same problem again and again by writing different kinds of problems. The more you practice, the more you will remember all these things, and you will see that you are doing it faster and faster and faster and correctly at the same time without making mistakes. Next, find the value of sine 15 degree. 15 degree is not a known angle, but we can still find the value by using our identities. We have sine 15 degree. The trick here is to recognize that although 15 is not a known value, but 45 and 30 are, and 15 is just this difference, 45 minus 30. So you have to use the sin x minus y formula here. Sin 45 degree cos 30 degree minus cos 45 degree sin 30 degree. So now you have to recall old values, school values. You are still in school, but you are about to go out of school. Sin 45 degree is 1 over square root of 2. Cos 30 degree is square root of 3 divided by 2. Cos 45 degree is also 1 over root 2. And sin 30 is 1 over 2. So this equals square root of 3 minus 1 divided by 2 root 2. If you want, you can do some things to this, but let me keep it like this. Do some things means you can multiply and divide by square root of 3 plus 1. That will change the numerator and then there will be some cancellation. But that's pointless. I mean, you have found it and that's it. And it's also that we do not have to show that this thing is equal to some already given thing. We just have to find it. So whatever you have found, this much is enough. But don't keep the answer like this. It shows that you just don't care. You don't care for what? You don't care for presentation. You should put it in a compact form. But you can stop here itself. Next, example, find again another such value of, but this time it's given in radian, 13 pi divided by 12. That looks like a very unknown angle, it is, but we will have to change it somehow like this. We have and since I am saying so many things about presentation, do not write SOLN like this, okay? You write, if you want to write solution, you write the full word solution. We have 10 13 pi over 12. Let us first of all reduce the numerator because it is just this, okay? And now we are ready to apply tan x plus y formula, but can we do so? You see, when applying these expansions, we did not in fact even think of whether we can do it or not, because we can. There is no restriction on the identities for sin x plus y, sin x minus y, those things. But when it comes to tan, there are restrictions. Recall that. The function tan is not defined for any kind of input. There is a restriction. And the restriction is that the angles involved should not be odd multiples of pi over 2, because those are precisely the points where tangent function is undefined. Are these odd multiples of pi over 2? No. Pi is in fact an even multiple of pi over 2, 2 times pi over 2. Is this an odd multiple? This is not even an integer multiple of pi over 2. It's less than that, pi over 12. So, no problem. We can apply the formula. And what is that formula? Tan pi plus tan pi over 12 divided by 1 minus tan pi over 12. But say you have started studying the example, because these things are already given in the text, and you don't remember this formula, there is no need to panic, because this is where you learn the things. You go back to what the formula is and simply apply it. The more you do it, the better you will remember what this thing is. Now this is 0. One minus 0. So the denominator is simply 1, and we will have, see, this is how we make mistakes. Tan pi over 12. Oh, and one more thing. Why is this 0? Because tan pi is sin pi divided by cos pi, and sin pi is 0. That is why. But now this is not a known angle, so what should we do? We can somehow, we should express pi over 12 as either a sum or difference of known angles, or maybe we have to consider multiples of known angles and their sum and difference. Luckily, it is just a sum. It's not a sum, it's a difference. Simply a difference of two known angles, pi over 3 and pi over 4. Am I correct? Because if I take LCM, it will be 12 and 4 minus 3. Yes. So now we have to again apply this time tan x minus y formula. Again you have to see whether these angles are odd multiples of pi over 2. This is not an integer multiple of pi over 2, it is less than pi over 2. This is also less than pi over 2, so no problem. We can apply our formula. For tan x minus y, we have minus here and the denominator has plus, the opposite of this thing. Alright, so let me continue on that side. So tan pi over 3 is going to be what? This is tan 60 degree. If you do not remember what tan 60 degree value is, it is square root of 1 over square root of 3. No problem, you just recall what tan actually is. Sin 60 divided by cos 60. Sin 60 is what? Square root of 3 divided by 2 and cos 60 is 1 over 2. Oh, so okay, so it is root 3, it is not 1 over root 3. So I was also going to make a mistake. So after you cancel that 2, it becomes square root of 3. Tan pi over 4, because that's 45 degree, is 1. Divided by 1 plus root 3 times 1. So it's just square root of 3 minus 1 divided by square root of 3 plus 1. Now again here also you can, if you want, you can rationalize the denominator. Those things you can do if you want, but I am keeping it like this because we have been asked to just find the value. Next comes another example. Prove that sin x plus y divided by sin x minus y is equal to tan x plus tan y divided by tan x minus tan y. When you see some such I should say careless identities, why do I make this remark? That's because we are not saying anything about how this term is not equal to 0, how this denominator is not equal to 0. We are not putting any restriction on x and y. See, there are two things that should be said about such expressions, such identities that you see in your book. Of course, if one simply writes something like this, that is in fact meaningless. Without any condition on these things, we don't really know what type of x and y are allowed here. In fact, you know what condition you should put here, but that's not given. So actually it's meaningless. That is one thing. That's the first thing. But the second thing is that then what is the purpose of these things? Are these things wrong? No, they are not exactly wrong. It is that at this stage, being so exact about these things that you have to take care of all the conditions. That's not the purpose at this stage. The purpose is to get you to use the identities to get what is given. Okay, it's to give you a practice of using those identities. That's the purpose. So those little things, that this should be a real number, so we should not divide by 0. Those things are pushed under the rug for a moment now. It's not that these things are wrong. If we in fact include those conditions, it will become a rigorous identity. But that's not the purpose right now. The purpose is to use the identities we have found to get this result. Okay, so let's see how we can prove this. And that is why, while using the identities in this type of problems, we should not really care about dividing by something, and there is no need to write also that this is non-zero. If you fall in the trap of going through those conditions, no, you won't really, you will get confused. So instead, let's just take the engineering approach and simply just do the proof without thinking much about these conditions. We have, and that is also the approach that we take when we study differential equations. For the first time, you will see in second year, in 12th standard, you have differential equations, and there also we are not so much, I mean in the beginning stages, we are not so much bothered about whether an equation, I mean if it makes sense mathematically, is it rigorous, those things are pushed under the rug when we study calculus and differential equation for the first time. Those things will again come back when we go to the college level. And the denominator, of course, is sin x cos y minus cos x sin y. And now, what do? We have to get tan. So that means we have to divide by cos. So cos x and cos y are the cos terms. So you divide by cos x cos y. Minus cos x sin y cos y. If you are still finding it somewhat not satisfactory, that we haven't really said anything about those conditions, you just assume that whatever you need is already there. Whenever you are dividing by something that is already non-zero, this is non-zero, this is non-zero, these things are non-zero, all those things are there in the background. So now, after we take this term below everything and do cancellation, what are we going to get? See, cos y and cos y will vanish. Sin x divided by cos x is tan x. What about this term? This time cos x will vanish, and sin y divided by cos y is tan y. In the denominator, if we see the first term, this time cos y will cancel out, and sin x divided by cos x is tan x. Again, minus. Now we have a minus. Cos x cancel out, and we have sin y divided by cos y, that is tan y. So yes, we are in fact getting what is given. Next example. Show that this one is very interesting. I mean, the form of the identity is very interesting. Tan 3x, tan 2x, tan x is equal to tan 3x minus tan 2x minus tan x. So this is the product of those tangent functions. This, however, is not a product. Okay, this is this one minus the other two. To prove this, if you want, you can start with the right hand side or the left hand side, but a better way is to start with this. In fact, we have tan 3x equal to tan 2x plus x. So we are not starting with an expression one side or the other side, but rather with an equation. And we will keep tan 3x like this because we need tan 3x. We are not going to say use the triple angle formula here. We won't do that. On this side, however, we apply the familiar tan x plus y formula. 1 minus tan 2x tan x, and after this also we do not do anything with tan 2x because that's what we need. We just have to, these are the terms, tan x, tan 2x and tan 3x, and now let's see what we get from this without changing those terms. So if we simply multiply both sides by this, then we get tan 3x times 1 minus tan 2x tan x, and the right hand side is simply tan 2x plus tan x. Now you have in fact started seeing what will happen. Tan 3x times 2x tan x. This is equal to tan 2x plus tan x. So now we are almost there. If you take this minus term to that side and bring these two terms to this side, then you have this. And if you want, you can write one more line where you switch sides, because that's how it's given, but you have your identity. Okay. Next, prove that cos pi over 4 plus x plus cos pi over 4 minus x is equal to square root of 2 cos x. Now this is now you see there are two ways of approaching this problem. You can either use your cos x plus cos y formula, namely item number 20, first identity, or you can just expand these things. It's up to you. Since nothing is given, so let's just simply expand it. Or in fact, actually there is a third way also. You recall the identities from 21. There, the first identity itself is what we need here. So if we do that, that's the quickest way. We have, so let me just write here itself, pi over 4 plus x plus cos pi over 4 minus x is going to be equal to 2 cos pi over 4 times cos x. So what is cos pi over 4? 1 over root 2. Let's see. But you do see in the textbook the cos x plus cos y formula has been used. That also you can do. Because we are in India, I don't know about other countries, but here, if this question has a lot of marks, then such a small solution won't get you full marks. That's the tragedy of this country. Actually, someone who is doing it quickly like this should get full marks. But the exact opposite thing happens. If say this one has 6 or 7 marks, it won't have that many marks, but I'm just simply saying, hypothetically say it has 10 marks, suppose. Then you have to write an essay for that. That is why we are in the current state. But anyway, next. Example, prove that unnecessarily long things are encouraged. Cos 7x plus cos 5x divided by sin 7x minus sin 5x is equal to cot x. Now we have been avoiding the item number 20, those formulas, for a long time in these examples, but now we cannot avoid anymore. We have to use them. cos 7x plus cos 5x divided by sin 7x minus sin 5x. Now we have to recall those formulas. Recall that when it comes to cos and cos, we either have cos cos or sin sin. If it is plus, then it's cos cos. So that is why the numerator is going to be this, cos 7x plus 5x divided by 2, and again cos 7x minus 5x divided by 2. The denominator, however, it involves only sin. So here mixed terms will come, sin and cos. Since there is a negative sign, it is subtraction, so cos and then sin. These things don't change. It is always this first and this afterwards. 7x minus 5x divided by 2. Now, cosine of this and cosine of this, same thing, and 2, so they cancel out. There is no need to write that. Now, what is 7x minus 5x? That is just 2x. 2x divided by x is x. Similarly, the denominator is sin x. So that's why this is cot x. Another one, this is, I think, the last one. Yes. This is the most complicated. Not really complicated, just a little long. Prove that sin 5x minus 2 sin 3x plus sin x divided by cos 5x minus cos x, and we should prove that this is equal to tan x. We have sin 5x minus 2 sin 3x plus sin x divided by cos 5x minus cos x. Okay. Now, what we will do, we will bring sin 5x and sin x together and apply the sin x plus sin y formula there, and this we will kind of simply keep like that. We won't really apply the triple angle formula here. You see, this kind of things actually can be figured out even before doing anything by looking at the angles. No matter which of the 4 formulas you are using depending on the situation, that is sin x plus sin y, sin minus cos, all those things, the angles, however, are always going to be the sum of the 2 angles divided by 2 and the difference of the 2 angles divided by 2, always. So you have to look at the angles. You see, if you combine this one and this one, you are getting 5x and x. So one of the angles should be 5x plus x divided by 2. That means 6x divided by 2, which is 3x. So you have a 3x here. So that may be fruitful. And that is why that's what we are going to do. And let's see what we get from that. Denominator, however, we have to just apply the cos x minus cos y formula. Okay, so in this step, we first bring the things together. Minus 2 sine 3x divided by, you can in fact start applying the denominator formula here itself. It is cos, but there is a minus sign, so sine will come. No mixed term, either both cos or both sine. Because we have a minus sign, so sine will come. And recall that there is a minus sign in front of that formula, the second identity of item number 20. Sine 5x plus x divided by 2 times sine 5x minus x divided by 2. Do not write the final value here immediately. Okay, you show these things. In the numerator also you accordingly have to show it. Now this is, the numerator however is sine. For sine mixed terms will come. And because you have plus, so it will be sine cos. 2 sine 5x plus x divided by 2 times cos 5x minus x divided by 2 minus 2 sine 3x. So now you can write, however, what it will ultimately be. So 6x divided by 2 is 3x. 5x minus x is 4x. 4x divided by 2 is 2x. And accordingly, the angles in the numerator will also be like that. 2 sine 3x cos 2x minus 2 sine 3x sine 2x. So you can see that you can cancel 2 sine 3x, which is available in the numerator, with it in the denominator. But of course there is a minus sign. That should not be forgotten. If you do so, the numerator will be cos 2x minus 1 divided by minus sine 2x. Okay, so now if you use the minus sign in the numerator, it becomes 1 minus cos 2x divided by sine 2x. 1 minus cos 2x, you recall your double angle formula is 2 sine square x, and the sine 2x double angle formula is 2 sine x cos x. So after further cancellation, you have this, which is tan x. So this way you have proved this one as well. and this completes all these examples of the section. So that means next we can solve the exercises of this section. And that's just it for tonight. So see you in the next upload. When will it be? Next Friday, calculus. So see you with that on Friday. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.